Welcome back to the Classics of Immunology Journal Club. And I just want to say up front, if you like this video, then like it on the YouTube channel and click on the bell to get notified so you find out when we do another one. And then also go on my website, kendallasmith.com, and look at all the information that you can get there, particularly on the writing tab, because you've got all of the papers, the classic papers of immunology have been reproduced there. And so you can read to your heart's content late into the night when you can't sleep. So today we're going to do another classic paper in immunology. I mean, they're all classic, but some are more classic than others. And this was published in Proceedings of the National Academy of Sciences in 1975. So 1975 was a banner year. So last week we had Kohler's and Milstein's paper on monoclonal antibodies. And this week we're going to do Lloyd Old's paper on the identification or of tumor necrosis factor, which becomes, as time goes on, a very important cytokine in the whole inflammatory response. So the authors of this paper are E.A. Carswell, Lloyd Old, and others. And Carswell, in terms of background, was the technician who probably did almost all of these experiments. And I've read other bios of Lloyd Old before. So Lloyd Old, he was the mentor. He went second in line. And there's several other people who were involved in the whole thing. But it's Carswell and Old that everybody talks about. And people are very laudatory for Old not putting himself either first or last, just going right after and giving Carswell the sort of the spotlight. Well, that was the 1970s, and as I've said before, that was before the Bayh-Dole Act, and you could make money
70s Raw on Amazon Music
from your discoveries. So Carswell was a technician, and Lloyd Old was, by this time in 1975, he has an interesting bio in that he graduated from medical school at UCSF out in California in 1958, and it says in a lot of his bios and so forth that he graduated first in his class, and then his parents bought him a Corvette that he drove across the country. He didn't do an internship in clinical residency. He decided he wanted to go into tumor immunity, and he wanted to go into science right away. And so he organized himself so that he got a postdoctoral fellowship at Memorial Sloan Kettering in New York. So he drove his Corvette across the country. And as they say, the rest is history. So that was 58. By 1975, he was 41, 42 years old. And he was an established investigator, and he'd done a lot of stuff in trying to work on this whole concept of the immune response to the tumor. And just to point out, there's a fair amount of history that a lot of immunologists may or may not know about. I mean, the whole tumor immunology thing starts with William Coley in 1893, when he reported that if he injected into tumors of his patients, first live bacteria, streptococci and so forth, and then later, when he lost a few patients due to the injection of the live bacteria, he used heat-killed bacteria, and he basically said that maybe about 10 or 20, 15, 20% of those patients, he could cure them. And of course, this was in the late 1890s. And as time went on, radiotherapy was introduced, and it sort of usurped the whole idea that you could use bacteria or bacterial extracts, which came to be known as Coley's toxins. And we reviewed that. We have on the Classics Journal Club, we reviewed that paper, and if you're interested, you go back and do that. So in addition, in the 20s and 30s, it was found that bacterial lipopolysaccharide, which is in the cell wall of a lot of the colon bacteria, when injected into experimental animals, would lead to septic shock. And people discovered that if the mice or the experimental animal had a tumor, that those often the tumor would undergo a hemorrhagic necrosis. And so that was reported. And that's what this paper that we're going to deal with today is really all about. And so that was a known entity. Then in the 40s, Jules Freund was looking for ways to augment vaccine responses, and he hit on the thing that if he used killed tuberculosis organisms and mixed them with oil and so forth, and then an aqueous phase that the antigen was suspended in, that he could get a heightened immune response and heightened antibody response to this whole thing. And that's where the whole idea of an adjuvant came into being. Well, throughout all of this stuff, these people started talking about adjuvants as something that they could add on to vaccines to make them work better, essentially. And today with the coronavirus vaccine, some of those vaccines that are out there, I can't remember which ones right now, but they use alum as an adjuvant, which is a very common adjuvant for humans. Then in 1969, so we're talking about this paper in 75, 1969, Georges Maté from France, from Paris, sort of rocked the cancer therapy world by a paper that he published in Lancet, where he said that if he inoculated patients with acute leukemia after they'd had a reduction in their, or they'd gone into remission from chemotherapy, then if he added immunotherapy, he said there were two different varieties, specific and non-specific. The non-specific was ultimately what Maté used was the TB vaccine, BCG. And that's what another thing that this paper is going to deal with today. One of the reasons that Old got involved in this whole thing is that when he came to Memorial Sloan Kettering in the late 50s, he's over the next few years, he was a young guy at Sloan Kettering, and there was another young guy who became quite famous in immunology, Boris Benesraf. And we've talked a lot about him. He went on to win the Nobel Prize in 1980. The Benesraf was investigating in the early 60s. He was at NYU. He wasn't at Memorial. Memorial's uptown about 60 blocks or 40 blocks or so. Benesraf was using BCG and so forth, trying to treat tumors and that sort of thing. And so Lloyd Old, got together with him, and that's really the genesis of his interest in using sort of immunostimulatory, non-specific immunostimulatory therapy to try to treat cancers. So that's the background. In the intro of this paper, this paper is sort of a weird paper. It's got a very short intro. It's only about 2 sentences long, and then it has. It doesn't have any materials and methods. It just has methods, it just has materials, and then the methods are put together with the results section. And then he goes on to a very short discussion. So most of the paper really is the method of trying to find this so-called tumor necrosis factor. And in the intro, basically what he says is that it's been an enigma in cancer biology for a long time, and he references William Coley and so forth, that some tumors would undergo hemorrhagic necrosis, and that can be induced by endotoxin or lipopolysaccharide. And then he quotes the papers back from 31, and then there was also some in the 50s. He then goes on to say that I'm going to read this. We report here that endotoxin acts indirectly on the tumor, causing the host to release a new factor that we're calling tumor necrosis factor, that is selectively toxic only for cancer cells. Those are his statements, bold statements, and this paper is supposed to corroborate those statements. And there's some problems with this paper, even though I say it's a classic, and it is a classic, but it's a weird paper. So the first thing he gives is he said that the assay for tumor necrosis factor is based on injection in mice of methylcholanthine-induced sarcoma that gives a solid tumor in the mouse, and that's important for this tumor necrosis factor. And he shows the results of this kind of an assay in figure 1 of his paper, and I'm going to do a screen share now on this. So in this figure 1 from this paper shows the results of a tumor necrosis factor assay, and these are mice that have had a subcutaneous tumor put just under the skin, and then this is scored with 1+, 2+, or 3+ of whether or not there's a necrotic center that appears in these tumors. So that's really it. What they did in order to do this is that they would implant the sarcoma 7 days previously, give it time to grow, and they found that when it got to be about 7 or 8 millimeters in diameter is when it was the best for this particular assay. And then they would inject intravenously 50 microliters of their TNF sample, and they would see this black necrosis within 24 hours. And that's also important. So within 24 hours, the tumor starts to go away, essentially. They go on to say that, and he goes on to say that about 25% of the mice injected, even though that they still have a necrotic center, they might still have tumor, but about 25% of the mice, they had regressions of the tumors. And they say there's no other side effects marked systemic toxicity, which is a little weird now that we know a lot about TNF. So that's it, and I'll take off this screen sharing now. That's what the assay appears to look like. And then he goes on in several different sections of this paper in the results section. Is that he goes in the second section, or the second point that he makes in this paper is that you got to have the mice infected with BCG first, and then you inject the endotoxin later on, and then within 24 hours of the endotoxin you get this necrosis. And he says that he tested a bunch of different inocula of the tumors. They're different size inocula, and he found that 200,000 cells was just right because it would give this tumor 7 or 8 millimeters within 7 days. They also did a lot of experiments testing how many BCG organisms they should have on board, and they found that 20 million live BCG organisms were optimal, and they had to have those on after 14 days of the injection of the BCG. You could bleed them and test for this TNF in the serum. And then also at that 14-day time, if you injected the lipopolysaccharide, and they used different doses of that, and they found that 25 micrograms was just right. And then if they waited 2 hours and bled them, they could get optimal TNF value, or optimal results in the hemorrhagic necrosis of the tumor. And they said that if they waited longer than that, like 3 or 4 hours, a lot of the mice were almost dead, and they were because they were undergoing shock, systemic septic shock. That's important in this whole thing, because that also had already been reported back in the 30s that LPS would cause septic shock, and that probably was the mechanism. They didn't pin it down, irretrievably, but it was probably the mechanism. whereby the tumors were becoming hypoxic because the blood pressure dropped out. So that you need both BCG, and what BCG does in these mice is that it really revs up the whole what they call the reticular endothelial system, RES, which is primarily the innate immune response with macrophages, NK cells, and all kinds of things, so that you've got a huge innate immune response going, and then you hit it with LPS, and that's when you get the hemorrhagic shock within hours after that. Then they go on and they show that they have, when they use different doses of BCG, they find that 20 million is optimal. And then the interval between the BCG infection and the LPS, they chose about 2 to 3 weeks so that you'd have the maximum RES stimulation. And they measured that by enlarged spleens and livers, hepatosplenomegaly in the mice. And then when they did these different doses of LPS, and then the time of the serum collection after all this business that they did, they tested within 30 minutes to 4 hours after the LPS and inoculated it intravenously into these animals, and they found that 2 hours was the best. And then the conditions that were optimal for the TNF assay, they found that if they waited until the tumors were well established, in other words, you could see them with your naked eye and you could measure them with a little caliper thing, that was really good. If you tried to do it early, then you couldn't find any tumors. It was too early. So again, you had to have a pretty big tumor, which now you know that a pretty big tumor is highly vascularized, because it brings in the blood vessels and so forth to support the growth of the cells in that tumor. So if you take away the blood from that by lowering the blood pressure, that's going to be a little bit of a problem. They said it also works with other priming agents. For example, the corynebacteria, 2 different varieties of those, and also yeast-oriented zymosin. They were just as effective as BCG. So anything to rev up the reticular endothelial system. They also used poly-IC that I used back in the day, which as an interferon inducer. It also stimulates markedly the macrophage component. They worried that there was just residual LPS in the serum of these mice when they were taking it to assay for this whole thing, and they tested that by 2 different assays, one a rabbit fever assay, and then another one is called the limulus assay, and it essentially was negative. So there wasn't residual LPS in the whole thing. They tested other tumors, other sarcomas, and even EL4 leukemia. If it was put in subcutaneously and formed a solid tumor, then that would work just as well as the methylclonthrine-induced sarcomas. There was a disseminated sarcoma that would go metastatic very rapidly, and the TNF samples didn't do anything to that. It's another thing that's got to have a solid tumor, well vascularized, and so forth. So they also tested other species, mice, in addition to mice. So they tested rats and rabbits, and they got a similar kind of a response. So the last piece of information that they give you in this paper is that they also tested their TNF serum samples. That it's just in the serum now we're talking about. They tested it for in vitro cytotoxicity on tumor culture cells, methane and so forth. And they tested L cells, methylclonthrine-induced cells, carcinoma cells, or sarcoma cells, and then mouse embryo fibroblasts. Now, L cells to me are basically a mouse fibroblastoid cell line that is sort of in between a cancer cell and a so-called normal mouse embryo fibroblast. But the L cells were very susceptible to this stuff in vitro. And the way they tested that was is that they would put their serum on these cells growing in culture, and they'd wait 48 hours, and then they would count the number of cells with a vital dye trypan blue that would stain the dead cells and leave the live cells unstained, which is a crude cytotoxicity assay. They went on from there. Other people went on from there to use radiolabeled target cells that then they would release the radioisotope, and they could count that in the machine. Anyway, on the basis of this in vitro test, they said there was always a parallel between the in vivo assay and the in vitro assay, which is one of the reasons that they say that they conclude then in the end that this is a selective toxin for cancer cells. And as time goes on, we'll see about that. So that's it with this paper. And in the discussion of this paper, which is quite short, they go back and say, this kind of phenomenon has been known since William Coley in 1893. And in 1952, it was hypothesized that shock was responsible for this LPS-induced hemorrhagic necrosis. And then they go on to say, but now we've shown that whole thing could very well be due to tumor, what we're calling tumor necrosis factor. And you have to remember now that we're not talking about a molecule, we're talking about stuff in serum. And there's a lot of proteins in serum. They said it's, in terms of other factors that might be induced in this kind of a situation with a revved up RES system, and then you hit it with lipopolysaccharide, is that they said it couldn't be interferon because they tested for partially purified samples and they didn't have any interferon activity. But that's the only thing that they looked for. And I'm wondering, so what happened to lymphotoxin? That had been around since 1968, first published by Gail Granger and Nancy Ruddles. They don't give them any press at all. They do go on, and they say that it's probably coming from a macrophage, although they couldn't be sure about that. And they also then reference Peter Alexander, who is an investigator in London, who had shown that if you activated macrophages in vitro with things like BCG and LPS and so forth, and then exposed those activated macrophages to tumor cells in vitro, that the macrophages would kill them. Well, they're suggesting here in this paper that the mechanism is via this soluble factor that they've named TNF. So that's the extent of this paper, and it's an interesting paper. You should read it and see for yourself what you think of it. The field itself was dormant, really. I mean, there weren't a lot of other people that jumped on the bandwagon here, and you have to wait a decade until 1985 when other people got into the act, and one of them was a group at Genentech, which was a new biotech company out in California, and they got the gene jockeys after the whole idea to see if they could isolate the gene encoding both lymphotoxin and tumor necrosis factor, or maybe there'd only be one. And so we're going to have to wait until we get up to 1985 before we review that. And another fellow got involved at that stage because another group, this time in also across the street at the Rockefeller University in New York, Tony Cerami, was interested in infections, particularly protozoan infections that caused the animals, they were chronic infections, caused the animals that were infected to become wasted And so he started looking in the serum for factors and found a factor that he called cachexin. And because it caused the mice or the animals to become cachectic, which is a word that means they just, they sort of got really bad, wasted. And Bruce Beutler was a postdoc with Tony Serrani, and he isolated cachectin and sequenced part of the amino acid sequence of this. By that time, David Godel from Genentech had successfully cloned the gene for what they were thinking was TNF. And lo and behold, there were some very interesting similarities, but well, that's in the future now. So if you like this journal club and if you're learning a little bit that might help you in your whole thing, click on the the YouTube site and the YouTube channel, and then the playlist for the classics. And then also click on the bell and look for the papers online on my website, kendallasmith.com. Thanks. We'll see you.